So I want to talk to you today a little bit about some analysis of the training dynamics of large ResNets. Okay, would like this to work.
Maybe I think it's the other one with my talk.
Oh, it's okay, it's okay. We'll just not. Okay, so we'll try to stick to a practical setting, so trying to stay close to practical ResNet architectures under standard learning algorithms. And the goal of today will be to first classify asymptotic behaviors, because before we want to deep into one particular limit of a training dynamic of a ResNet, we want to classify them and see which ones may be more interesting. And this is also useful to, in practice, understand how to scale the hyperparameters of training, such as initialization scales or learning rates. And the main focus today will be on deriving tight quantitative error bounds towards the limit. And I will argue that this can be helpful to understand what is the optimal way to shape an architecture such as a ResNet. When I say transformer, I mean, I'm thinking of ResNets. These are like a particular kind of transformer, of residual architecture. The key keyword today is residual neural network. So before we dig into ResNets and all this program, I want to derive the story for the two-layer neural network case. Because as we will see, once we have understood two-layer neural networks, we are almost halfway towards understanding transformers, because there's a lot of phenomena in common. So let's start with this setting. So we'll focus on two-layer perceptron architectures with input and output dimension capital D. So here notice that I'm also taking a large output dimension. I mean, potentially large, but at least but much smaller than the width, because of course the idea later when it will be to stack such architecture to form a ResNet. So we need a same a large output dimension. So two important quantity, capital D and capital M, which is the number of hidden units in the architecture. And we can write the function parameterized by a two-layer perceptron like this, with a non-linearity rho. Throughout this talk, rho will be a function with bounded first and second derivatives. These are the assumptions we'll need throughout. And I'm putting here a 1 over m factor in front of the sum. If you don't like it, we can remove it. And in fact, what determines the scale of this sum is the product of the scale of v times 1 over m. So you can always change the, remove this factor and scale v differently, but this will be more convenient later. And so I'm choosing a loss. I'm assuming that the loss, like this condition here is a natural way to ask that I want to make the loss decrease by theta of 1, I need the output of the neural network to move by theta of 1. So that's a natural condition for the scaling that we will assume here. And we want to study a gradient descent from a random initialization. So I'm sticking to gradient descent for simplicity here. And the initialization as standard deviation sigma u for the input weights u and sigma v for the output weights v. I will always use these kind of notations. Of course, the initialization is centered. And we have also two other learning rate parameters, eta u and eta v. And once we have this dynamical system, the question is, how does it behave? Like we do k steps of gradient descent. I will not care about long time behavior today, only a fixed number of gradient descent steps, and we want to understand how it behaves. So for two-layer case, we will focus on the regime where m is much larger than d, okay? So we need to decide what are good choices of these hyperparameters. So for the sigma u, the initialization scale of the input weights, we choose 1 over square root of d, because this makes the proactivation at initialization of order theta 1. This is a natural choice. For sigma v, it's not clear a priori what to do, so we'll do a phase diagram. Okay, we'll see how the neural network behaves as we vary sigma v as a function of its scaling in d and m. And for the learning rates, there is a natural way to always normalize the learning rates, which is to ask that the loss decay at in theta of 1 when I mean, whatever the scale of the neural network. Okay, so we are asking that this is the loss of the decay of the loss due to the input layer weights. I'm asking it to be theta of 1, and the decay of the loss due to the output layer weight also should be theta of 1. I'm taking the max between the first and second gradient step because sometimes at 0, if I have sigma v equals 0, there might be some difference of scaling, but at time k equals to 1, this should normalize properly the loss decay. And if you have like Adam or other algorithms, you can replace this by the loss decay. For instance, for sine gradient descent, this would be the L1 norm of the gradient. Okay, so I will always normalize learning rates using such normalization in the talk. And so the question is, how does neural network behave as a function of the single hyperparameter that remains, which is sigma v? And we have this phase diagram. So here sigma v increases like from 0 to plus infinity. What I'm plotting is in fact sigma v divided by m, which is this scale of the output of the two-layer neural network. And we have these phases. When sigma v is 0, we are in some feature learning regime, which means that the activation changes in theta of 1, at least in the first gradient descent step. Typically, it's a bit subtle to track this later, but at least later we can guarantee stability of the dynamics. So we have this regime. And then there is some phase transition, which we can call the maximum diversity feature learning regime. Or I can call it also the critical scaling for this two-layer neural network. And when we are beyond this scale, the behavior of gradient descent is described by this lazy kernel regime where the activations change in little o of 1 at any step. So why does this happen? It's because the output layer weights, this V, are too large, and any small modification of the pre-activation will be amplified by the output layer. And if I change the input weights too much, I will make the output of the neural network explode. So you have to decrease the learning rate, which is automatically done via this criterion. And you're in this lazy kernel regime where only the first, you can linearize the neural network around its initialization. Then you have this scaling at 1 over square root m, where the first output is bounded by the central limit theorem, and beyond that you explode. Okay, so that's the various phases that we have. So that's the first step when we want to analyze the dynamics, like to identify the phases and then study in detail what's going on in each of these phases. So now what I will do is write the equations on this blue and green phase. Okay, this is the same phase. The blue is just like the critical regime where we are changing from one phase to the other. So these are the equations of the limit model when we are in this feature learning regime. So there are several ways to write it. This is the form which is convenient for this talk. I replace the sum of m terms by an expectation. And here the parameters are now random variables on some probability space, which is an abstract space. Random vectors in RD. And you can write the predictor like that, like an expectation. And then if you're doing gradient descent in L2 on these random variables, this is exactly the limit model that you get in the first regime where you're in the feature learning regime. So often these equations are written in terms of the law of UK VK, which then corresponds to some Wasserstein gradient descent, but I will not use this framework today. And the question which we can ask is, how fast do we converge to this limit? And in this case, this is the rate of convergence we can obtain, and this is tight. I mean, if you do numerical experiments, you would notice this rate. So here, HK hat is the output of the finite neural network after k steps of gradient descent, and HK will be the output of the limit model after k steps of gradient descent. Under this feature learning regime, so which corresponds in particular to sigma v big O of square root d, this is the RMS, like the typical distance error on the output, on the entries of the output. It's of order sigma v plus 1 over square root m. Okay, and here the big O, throughout this talk, it will hide some quantities which depend badly in k, in the number of training steps. This is not something that I will try to fix in this talk. And there's I will also skip the details. These are high probability statements. So for some probability, typically we have like here, this would be a sub-exponential concentration on this quantity, but I will not write all the full results, only these simplified versions. So what we notice is that if sigma v, the output layer scale, is square root of d, we converge to the mean field limit only if m is much larger than d. Often, in the literature of two-layer mean-field neural network, it's said that the convergence is dimension-free, which is the case if sigma v is big O of 1, and this is a typical setting that you can have when the output dimension is 1 or bounded, but when you have a large output dimension, so I don't want to argue that for two-layer neural networks it's important to have this scale, but when we'll stack several two-layer neural networks, it will become important. So we are more interested in this regime where sigma v is square root of d, and in this case the convergence only happens if m is much larger than d. And I will only show convergence on the prediction function, but also throughout the talk, we have the similar results of convergence in parameter space, like on the actual parameters we train, if you do a suitable coupling throughout training. Okay, so that's the first part of the phase diagram. Then we can move to the next phase, which is this lazy kernel regime. Yes, question?
So you are doing gradient descent on the population level, right?
What I'm doing, okay, I don't really have data. Like I don't look at the structure of the data. I'm just taking a loss, and you can assume that I have a finite number of training points. I don't distinguish between training or testing. So let's say you have a finite number of training samples, and I'm doing a gradient descent on the empirical risk. Yeah, and I'm not scaling up the number of training samples. This would change slightly. This will change the story. That's an important point, yes. So in this talk, we will not focus on the structure of the data. It will be only about what happens inside the neural network. These things are, I mean, it's a blessing and a curse, and at the same time, it means that what we're saying is universal in all kind of settings. This will be relevant, but of course, we are missing some structure when the data has some structure. Okay, so we can write the equations in the regime where we are in the lazy kernel regime. So as I mentioned previously, the input weights will move only infinitesimally from their initialization in the limit. And then you can do a first order Taylor expansion. This is how it will read. And you do gradient descent on this Taylor expansion. You have equivalence with the gradient descent of the finite width dynamics with some error terms. So we have the same error as before and a linearization error. I will not enter into the detail for this phase because we are mostly interested in the phases where we have feature learning. But it is to mention that in each of the phases, we can do an analysis. So let me summarize what we have for two-layer neural network. Now we will move to ResNets. We have, as a function of sigma v over m, the total output scale, we have this phase from feature learning, then some critical scale corresponding to the maximum diversity feature learning, by which I mean that there is the maximum randomness at initialization. This is, I remain informal for respect to this notion of diversity. And then when we increase the scale, we go to this lazy kernel regime, then NTK regime, and explosion. And two things to keep in mind is that in this regime, when I'm at criticality here in the blue strip, convergence requires m to be much larger than d. Okay, and also the criticality at initialization is not like the critical scale at initialization, which is this one, before which beyond which I have explosion. It's not the same as a critical scale for training. In a sense, at initialization, all the randomness is completely pure, so you can have much larger objects and still have convergence of the sums that are involved. But once you train, you'll have some quantities which will correlate to each other, and you can afford a much smaller scale of the objects before the output to somehow explode. So criticality during training is not the same as at initialization. Okay, do you have questions? Like this was to set the stage, but we will use all these concepts for ResNets. Okay, so let's look at the main architecture of ResNet which we'll be concerned about. So let's fix the notations. This is represented graphically here. It's a ResNet with L layers. So this is here the number of blocks, which is 8, I think, in this plot. The hidden width is the size. So the architecture we'll consider is a ResNet, which means at each layer, I'm adding a two-layer perceptron to the previous output. And M will be the width of each of these two-layer perceptrons which I'm adding. So this corresponds to the number of points per layer, which is 5 in this plot. And capital D is the embedding dimension, which is constant throughout the ResNet. And it is represented by these 4 lines here in this plot, which is 4 in this plot. Okay. These are the main quantities, and we will talk about these throughout the talk. So LMD, let's keep these notations in mind. Otherwise, this is the same as taking two-layer perceptron. Notice that I've put here a 1/ml factor in front of the sum. So the scale, the total scale of the residual block here will be the scale of V divided by ML, okay? And we are making the same assumption on the loss and on rho. So we're gaining a bit more complexity than before. Next step in the talk will be to consider a transformer, but for the moment, let's stick to that one. And I'm considering gradient descent, again with random initialization. This is the same equations, except that now I have one more index because the U's and the V's, we have one such matrix per layer. So we'll still use the balanced contribution learning rates to normalize things properly. And sigma u, the input scale, the scale of the input weights will also be 1/square root of d, so that this sum, like this dot product, which is a sum, is θ1 at initialization, and so the activations are θ1 at least during training. And we will do a phase diagram in sigma v. Okay, so now, before going towards that, I will mention a bit the kind of analysis that have been done on our networks on ResNet. So I will be very brief. There's a lot of things, of course, and I cannot do justice to everything. But okay, we can classify somehow the approaches in the ones which is the oldest signal propagation literature, which looks at the first forward pass through a ResNet, or the first backward pass when you study the neural tangent kernel. For training, we have to be careful that having a critical scale at initialization is not the same as a critical scale during training. So the insights we get from this signal propagation analysis cannot always, and in general, cannot be transferred to training dynamics. There is also this viewpoint that sees ResNet as neural ODEs. So if you look at this literature, it really consists in seeing the ResNet as a discretization, standard discretization of a ODE. But for this to be true, you need the same weights throughout layers, or at least weights which are discretized, the discretization of a regular Lipschitz function of a function of depth. So this does not apply to standard ResNets. Then there is a large literature that uses tools from statistical physics, in particular by the team of Cengiz at Harvard, that have models for infinite size ResNets. And in fact, in part of my talk, we will use similar tools. So I mean, this is a very powerful tool, and that's a good way to analyze ResNets. But in the previous literature, some things which have, up to my knowledge, not been studied is decoupling D and M. So generally, we see that D scales as theta of M. For our analysis, it will be important to separate these two quantities because, in fact, we'll see that M is more naturally coupled with L, the depth. That's what I will argue for. And our focus is on quantitative and sharp bounds of convergence to the limit, because in the end, we'll want to have the optimal size. Another line of work is the mean field neural ODE, and this I will present a bit later. This consists in taking infinite width two-layer perceptron at each layer of the ResNet and taking also the depth to plus infinity. But as I've mentioned previously, this only a priori applies when M is much larger than D. I mean, this analysis is valid only if you fix D and let M diverge. But now if we look at, let's say, a standard architecture here, this is a Llama 3.1, a large language model from a few years ago. And they have like 3 models in their family of 8 billion, 70 billion, and 400 billion parameters. And these are the corresponding parameters they have for the MLP blocks. You see that M over D does not diverge. So we are not really in the regime where the hidden width is much larger than the embedding dimension. However, there's one quantity that diverges, which is M times L divided by D. And when you look, so this is this family of model, but when you look at any frontier model, you see that when they scale up models, this quantity will diverge to, will be large or diverge. So we'll be interested in this regime, and this is the setting of our analysis. We only want to require ML much larger than D. And we assume that the object we'll obtain in this limit is the ideal transformer or ideal model. And so the question is, how can we approximate this model efficiently? Okay. So let's first, before heading into the error bounds, we want to identify the phase which is interesting for training. So this is the phase diagram. So here I recall the phase diagram for two-layer perceptron, because as you will see, there is something funny happening for these kind of ResNets, is that if you replace M by ML, which you can interpret as effective width, you have a very similar phase diagram. So here this is the phase diagram for the ResNet. The horizontal axis is sigma v divided by L times M. So that's the scale of the residual block. And you have these various regimes that start from a complete feature learning regime. So this was identified in a paper by Day and co-author, among which Boris, Cengiz, so people in this room, which is a regime where feature learning is not really the good quantity you want to track in ResNet. What you want is that the weight matrix at each layer contributes in a non-negligible way to the change of preactivation of the same layer. So you want local feature learning. When you have an infinite number of layers, this becomes an important distinction. And they have observed in this paper that this leads to better performance in practice when you have this behavior. So they have a hyperparameter transfer and so on. So this is the relevant characterization of feature learning that you want to happen in a deep ResNet. And they have identified that this transition was related to the scaling 1 over L. So here, since we want to decouple M and D, we need to be slightly more precise, like to separate the role of D and M. And this is where the transition happens, that's square root of D over LM. And beyond that, you have this lazy ODE regime. I will give the equation later, but this really corresponds to the lazy kernel regime, except that what you're linearizing is the right-hand side of your ODE instead of the whole model. And, okay.
So can I just interpret this? So like, what's the x-axis? Is that sigma v or sigma v over LM?
This is sigma v over LM. Yeah. So let's say if I didn't put LM, that's the scale square root of D over LM. So what we can see in your paper is 1 over L square root M. Also, M equals to D. So that's the same thing. Okay, maybe this criticality at initialization, this is 1 over square root LM. In this case, the first forward pass is described by an SDE, and it's much more difficult to analyze the training dynamics. In this case, I think this is, there are some descriptions in Bordelon et al. Papers, and it is in this regime. So if you have a nonlinear block, you will be linearized. Okay. So that's what we will care about is this regime. Okay, so maybe I can give one quick rule of thumb to understand where this comes from. There are several ways to identify the phase transitions. That here there's one way which uses the fact that there's a relationship between the change of the preactivation due to a certain weight matrix during one gradient step and the change of the loss and the backward pass received by this preactivation. So there's a general formula which works in any architecture. You can apply it. And if you use that the change of the loss due to one weight matrix is 1 over ML because we have this balanced contribution learning rates, you look at the scale of the backward pass that is received by this preactivation, and you obtain that the change of the preactivation due to a weight matrix is square root D over sigma V, which shows the criticality at this scale. There are other ways to identify this critical scaling, but what we will see when we analyze the resulting model is that there are many things, like all the estimates that we will derive that are needed in the analysis, they explode exactly at the same level, square root of D, and before that, everything is well behaved. So now let's talk about the large depth limit. So I mentioned previously that there was this approach for large ResNets where you take both infinite width of each of the two-layer perceptron blocks and infinite depth. Okay, so this looks like that. It's like an accordion-like architecture, which is not what we have in practice, but we can still wonder what is the limit. So both we'll have, because we have infinite depth, we'll have ODE behavior, and since we have infinite width, we have mean field behavior. And so what you will have in the end is some ODE that describes the limit model, where the right-hand side of the ODE is exactly a two-layer infinite width, two-layer perceptron. So that's exactly the equation I had for the two-layer perceptron in the limit, except that now the parameter v is not a random vector, but it's a random process indexed by s. S is the index of the depth, which goes from 0 to 1 when I go from the input to the output of the ResNet, okay? So this is the limit model. But as, like if we gather the insights we have seen for two-layer perceptrons before, if we are in this regime where sigma v is big O of square root d at the critical scale, then the error rate would be the sum of two terms. I mean, here I'm simplifying a lot. The proof wouldn't be that simple, but that's what you would get. You would have one term, 1 over L, which comes from the depth discretization. This is like the error of Euler scheme. And square root of d over square root m, which is the error of approximating this infinite width two-layer perceptron. And here I cannot, even if sigma v was 1, in fact, I would still pay square root of d. I'm being a bit fast here, but it's because you pay for the fluctuation both in the forward and in the backward pass, while in the two-layer case, there were fluctuations only in the forward pass that were important. So here you cannot, even if you choose sigma v equals 0, you cannot escape the square root d over square root m. So this does not converge unless m is much larger than d, which we have seen is not the practical setting. So this, either this is the wrong limit or this bound is loose. So what is happening? Let's look at some experiments. So the question we have is, we start with the large depth behavior, we'll see later for large d, of a ResNet, okay, but with m of order d. We don't want m to be much, much larger than d. And in fact, we can even push the question further and ask ourselves, what is the limit if I have m equals to 1? So that's apparently, that's just for the sake of theory. I'm not saying this is a good model you want to train. But does it have a limit? And if yes, then that should put us into, suggest some ideas. So here, what I will plot will be a video. I will plot the training dynamics of a ResNet of m equals 1. So hidden width equals to 1. And this is the forward pass on one of the training samples. So the depth, like this is the input I'm giving, and this is the behavior of the forward pass. The target label is the orange blob here. So during training, we should match this label. And so I'm training with 10 training samples in dimension 10, but I'm only plotting one, and it's one-dimensional projection. So let's look at how it behaves. So there's not much to say when we have here, the depth is 200. So there's not much to say, except that it seems to converge, which is a good news, but no one knows why. Okay. I mean, no one knows how to prove that it's the case in general. Now I will increase the depth and I will go to 900. Okay, so it becomes slightly more regular and still behaves well. And let's increase the depth again. So I will restart. And now this is depth 10,000. Becomes very regular. So we see that it looks like starts looking like an ODE, in fact. And if I compare with the neural mean ODE, which is the dynamics of an infinite width ResNet, we see that it converges to that. So here I'm comparing a width 1 ResNet with an infinite width ResNet. But in both cases, the depth diverges. That's the reason for the title, is that there's some hidden width into a deep ResNet. So here I'm plotting all this is the result of one training run. Each curve is the result of one training run with the same convention as before, with depth going from 0 to 10,000. And we see that as depth increases, we converge in some random way, but to the dynamics. I mean, this is the result of the dynamics of training of the neural mean ODE. So that's what we want to explain with the first theorem, and this is this theorem, which says that if we are in this critical scale sigma v of order square root d, here there's this condition which I don't think is necessary, but makes the proof much clearer. So I assume that m is not much smaller than d. Okay, it can be much larger, it can be of the same order, but not much smaller. I don't think it's necessary, but let's put it. Then with high probability, you have the bound 1 over L plus square root of d over square root of ml. So once again, what matters is not, I mean, you have the same behavior as the two-layer neural network, except you replace the width by this effective width, which is the product m by L, which is the total number of nodes you have in the neural network. And you see that even if you put m equals to 1, this converges to 0 when the depth goes to infinity. And if you want to know where this square root d comes from, you can decompose the contribution of sigma u, sigma v, like the scales of the initialization of the forward and backward pass, Okay, but you'll pay square root of d in any non-degenerate limit. And when you compare these rates with practice, so here I have fitted the trends with some coefficients and compared with practice. When I vary m, l, or d, we see that it's tight. Okay, so that's the tight error rate, at least empirically, in terms of L, M, and D. Okay, so I will give a quick idea of the proof. How does that work? Let me check the time. Okay, good. So the basic objects that we care about in the limit, or that appear in the limit, these are ODEs of the following type, where the right-hand side is given by an expectation. And here zk, you can think of it as the parameters uk, vk, all stacked together at time k. So this is a random variable that contains all the random parameters. Sorry, that contains the uk and vk. And this is the ODE that I get in the forward pass of the neural mean ODE and on the backward pass as well, with different phi. Okay, and we have somehow such a discretization where I'm doing Euler discretization in S, but also I'm doing Monte Carlo approximation for the expectation. So here I'm simplifying, of course, because I will assume that ZK, like all these that appear here, are IID. This is not the case at all in ResNet, but I mean, that's the case at initialization. But let's first discuss if we had IID sample, and we were using such a discretization of the ODE, what would be the convergence rate? Well, we'll have this 1 over L, which comes from the discretization of the explicit Euler scheme, and the constant in front of the 1 over L will depend on the regularity in S of the object. So in particular, to derive the bounds, we need uniform, I mean, you need tight controls on the Lipschitz regularity of the parameters as a function of the depth. And then for the second term, it arises from the discretization of the expectation, and this is like a typical Monte Carlo rate. And to control what is in the big O for this term, this is the variance of this function phi, or more specifically, we're using sub-exponential or sub-Gaussian concentration, depending on the exact settings. For the architecture I've shown, this is sub-exponential concentration. So we need also to understand properly how the sub-exponential norm of these kind of random variables behave in the limit model. Okay, so this is what we get. And here there's a nice analogy with what's happening in the one forward pass of a ResNet and the behavior of stochastic gradient descent with batch size 1, or let's say batch size m. The fact that when you have SGD and you take a smaller and smaller step size, the trajectory converges in some sense to gradient flow and the population loss. Okay, and this is a very similar idea than here. In this analogy, 1 over L, 1 over depth plays the role of the learning rate of SGD, and the batch size of SGD is exactly m. And so we know that SGD, even with batch size 1, converges to gradient flow and the population loss. This is the same kind of mechanism. And later, when we discuss the optimal shape, you should also keep in mind this well-known fact that SGD, with a fixed computational budget, it will not approximate better gradient flow if you take larger batch sizes, because it costs more to compute the gradient on a large batch size, but it helps to parallelize the computations. And this is the same phenomenon here. Taking a large M only helps in parallelizing the computations. You will not reduce the error for a fixed product ML, which would be the computational budget here.
Okay, yeah. So like, I thought that you were going to scale the sigma V's to be like root D.
Yeah, they are.
But then, like, doesn't that make the scale of the phi's an extra root D bigger?
That's a good question because it takes 15 pages in the paper. So I'm glad I mean, it takes a lot of effort. I mean, so no, I mean, phi here is just an abstract function. In our case, this is for the forward pass. This is, I mean, the function of the forward pass. Yeah, exactly.
But I'm saying that thing seems to have scaled root D when you scale V that. Like, I would have thought you get an extra root D in front. And then
I mean, there is a root D. That's where the root D comes from here. Like in the error, this is root D here. So, but that's so subtle. I mean, I'm not saying it all comes up in the same place, but the root D exactly comes, I mean, from these fluctuations, which are of order square root D at this scale. They are not in front of the 1 over L because the Lipschitz regularity, this one is uniform in the, so you need all these kind of controls on the limit dynamics to make sure that you get the good scaling. But yeah, that's exactly, yeah, the square root D comes from there. Okay, so that's in the ideal setting where we had IID samples at each steps of the limit model. This is not the case. So now comes this general toolbox of propagation-of-chaos analysis, which comes from the analysis of interacting particle systems. So the parameters, so here this is again the UK, VK at all training steps, all depth, all indices J. They are not independent. So what we do, we start with independent ones. I mean, that's the random initialization. And we couple the dynamics between the limit model and the finite size ResNets. And we make sure that the error between the two does not grow too fast. So we go through this mechanism, like we take such a result, like we need to have such a convergence result with error terms. And we do the mechanism, forward, backward pass, and control the errors. And in the end, over a finite number of training steps, things go well. But of course, we have bad dependencies in the number of training steps we are doing. Okay, so that's like an interacting particle system, but the number of particles is ML, and one particle is like a path from a stochastic process. Okay. I will go very briefly. We can do a similar thing on the other phase, which is the lazy ODE phase. Here, the limit model is the neural mean ODE, but the right-hand side is linearized. And you get some error terms I will not detail. Maybe here one comment. This is about another phase. Here, this was for the lazy ODE phase. Here, this is if I am before the critical regime. So if sigma v is smaller than square root d, than sigma v, we might wonder if it's like a good choice. I mean, what we can see from the analysis is that as d goes large, you get exactly the same dynamics as if you had initialized sigma v with 0. And here, there's clearly a loss of feature diversity, like if you initialize the output weights of each ResNet block with 0. If you're not at the critical scale sigma v equal square root d, then you will eventually be equivalent to having initialized at 0. So that's why it's important to be exactly at this criticality scale. Although, I mean, understanding why it's important to have diversity of feature, at the moment, I'm being very vague. This requires much more understanding here. Okay, so maybe questions on ResNet before I move to. So now what we will do is also take the large D limit. Okay, and I will be a bit brief on that. Okay, so first a comment on the fact that the structure of transformers is essentially the same. Modulo, we do the proper identification. So transformers are ResNet architectures where we alternate between MLP, like I've shown, and attention blocks. So it's a bit trickier in the notations because the inputs has 2 dimensions. There's the like the dimension of the embedding and also the number of tokens for transformers. But here I'm assuming that the number of tokens is fixed, so it's a constant. Then you can write the attention block. Its general form is like that. You have some value, query, and key matrices that act on your input of the layer. You apply some nonlinearity, which is a soft argmax, and then you have some output weights. So if dk, which is the dimension of output of all these matrices, is fixed, so let's say you're constant, then we have exactly the same structure as before. So here I'm twisting a bit the analysis because in practice dk is quite large, it's like 100, but it's generally not scaled up if you look at also a model what is done in practice. So it's not clear whether scaling up dk is very important or not. But at least if we consider dk, the dimension of outputs of all these matrices to be fixed, then we have a similar structure as before. And also I need to assume the same regularity on the nonlinearity, the same assumption on the nonlinearity as before, which are not satisfied by the usual soft argmax. So modulo these things which require further analysis at a formal level, this is the same structure. And in particular, in an attention block, what plays the role of M is the number of attention heads. The role of U, the input weights, is these 3 weight matrices, and V is W. So you can use the same scalings and obtain the same error rates. And if you alternate between MLP and attention layers in your ResNet, the limit ODE will have two terms, one term for the MLP blocks and one term from the attention blocks. Okay, so that's the limit infinite depth of a transformer. Notice here that we have two extra operations, which are the embedding and unembedding matrices that take some input and put it in some dimension, the embedding dimension, capital D. So we see that capital D is also something we can act. It's a parameter of the shape of the architecture. It's not something that comes from the data. We can like the data has some fixed input dimension, but the dimension capital D where the ODE takes place is something which is also a hyperparameter of the model. Okay, so now I will talk about work in progress. So this is not in the paper that I've talked about, but we can start from this ODE and study each large capital D limit. Okay, and like what we can see is that you converge at a somehow 1/square root of D rate. Right now we have a log D. I'm not sure if we'll manage to get rid of it, so I still leave it for the moment. So you can decompose the error between your finite transformer and the transformer where everything is infinite, so L and D are infinite, M, you can take it as you want. You can decompose it using the triangle inequality. You have the finite model and the one which is infinite depth, so the neural mean ODE, and then the convergence of the neural mean ODE towards its limit, which is this other term. So the first term is the one I've discussed previously, and this is the second term, okay, which corresponds to the taking the large D limit of your transformer. And now we see that there is a trade-off in D, so I will ignore the log in all my computations after, which you can optimize in D and find, that the rate is minimized when D is of order square root of ML. Okay, so that's one first relation between the hyperparameters we can have to minimize, like to approximate the limit as fast as possible. There's another criterion which comes back to the parallelism idea that I mentioned previously, is that you want to take the depth as small as possible so as to maximize parallelism in your model, but you don't want to increase the error. So you take 1/L, I mean you take the depth so that 1/L is of the order of the other errors. So that gives you another relation between the parameters. And when you use these two relationships, you can fix yourself a number of parameters P, which is L times N times D. And you use these two constraints, and this gives you this shape, like the scalings of the shape to use for a fixed number of parameters P. So the hidden width here scales as square root of P, the depth as P to the 1/6, and the embedding dimension as P to the 1/3. And when you use these scalings, this is the scalings that minimize as fast as possible this upper bound, and you get a rate in P to the -1/6. Okay, so it's very slow, but it's not a good thing to converge very quickly for when you have a model, when you want to use and exploit the fact that you have a lot of computational power. Converging slowly is a good thing in a sense. Yes?
So why is this necessarily the limiting object? Why is that necessarily a good target? Like why do you want to?
Yeah, that's like the main, I'd say, hypothesis throughout the talk. I'm just looking at the table of the models, let's say like the Llama 3.1 model. I observe that people, when they have more computing power, they train bigger models, and they train it in a way where LM is much larger than D. So I'm assuming that the limit model we get in this limit is good. Of course, this requires, I mean, empirical investigation, and I don't have the computing power to do that, but that's like a hypothesis which I accept as a starting point. Yes?
So does this imply that so the common practice of scaling like heads linearly with the embedding dimension might be too aggressive? Like you could
yeah, kind of, yeah. So of course, this is the optimal scalings. I mean, optimal, assuming the upper bound is tight. If you are in this critical parameterization regime, in practice, this is not used in general, like this 1/depth factor. So I mean, maybe with those different hyperparameterizations, which are a priori not optimal, you might get different ways to approximate the limit. Yeah, but if you use this critical scale, this is the way you approximate the limit as fast as possible. And yes, in practice, since M is of order D, I mean, this suggests that you can take much larger hidden layers, but you need to put the 1/m here to make it work, which is like the scalings we have. In practice, people use 1/√m kind of scalings, and it will not work as you would like if you upscale M too fast without using the proper scaling. So there, you need to take everything at the same time into account. And so I will just conclude on this small plot. So that's what I can do in terms of computations. So it's like it's just a ResNet. It's not a transformer. So I remove the attention blocks. And this is the RMS error after 15 gradient descent steps. And so I approximate the limit with like a large ResNet with a few hundred million parameters. And I compare various scalings. So the ones which is optimal is in orange. In blue, this is a different scaling of D as a function of P. So sorry, in orange, we see that it's P to the -1/6. It fits the line, so this shows that the upper bounds are tight. Now, if I use, let's say, D of order square root P, it means I'm splitting the parameter count as much between LM and D. So I'm in a different regime because now D over LM will not go to 0. So this is a different limit, and that's why it converges to something else at the end. And for the one in green, this is intermediate between the two, so there's some non-asymptotic effect where it approximates the red limit quite quickly, but then you get the predicted rate after some time. So at least for short training times, these upper bounds appear to be tight. If you were looking only at initialization, you would not see at all this. So all these aspects come after training. At initialization, you converge at very different rates, much faster than 1/P to the -1/6. Okay, so that will be all. I will conclude quickly. So the main things I've discussed today are these phase diagrams and the error rate in LMD for ResNets. And the general messages which I can pass. First, I was very surprised at first to see that there's a lot of similarities between large ResNets, very deep ResNets, and two-layer perceptrons when you compare their phase diagrams and their error bounds. So it's worth studying in depth the two-layer models, which a lot of us have done in the past. So I think it was a good news somehow. And also, I think, this shape scaling that I've shown, I think it's just a first step, and it's, I think, a rich area for research in the future. Okay, so that will be all for me.